Hello everyone. In this lecture, we are going to learn about two types of equalization methods. One is called linear equalization and one is called nonlinear equalization. So that we can able to understand the importance of the equalization in our communication system, where we deal with signal propagation and receiving by means of antenna, the receiving spot, where we need to concentrate on the quality of the signal. So the quality of the signal means we will always tends to have a signal with good SNR, that is the signal to noise ratio. And secondly, we can able to know the type of the equalizers. So basically we know that we are using the equalization technique as a signal processing method in order to minimize the effects caused by the distortions, because we know that this kind of problems actually bringing change in the amplitude and the delays. So the signal which we now tends to receive, there we need to minimize these kind of effects. So the main term is intersymbol interference. So we have an equalizer, the name is linear equalizer, which is called by the name transversal filter, because in all the equalizers the filter coefficients are adjusted, linearly weighted to get the output. So in linear equalizer, the current and the past values of the received signal are linearly weighted by the filter coefficients. So the current and the past, from that the sequence of the samples and the symbol rates, we can able to adjust and we can able to produce the output. And here as usual we have the delays and tap gains, and if they are considered as analog, the continuous output of the equalizer will be sampled at the symbol rate, and we can able to from that samples we make the decision, because we know that in the decision maker is important, which determines the value of the data bit, that is a digital data bit which we need to receive, and based on the threshold value which we set on this, we can able to extract the correct output. So anyway, overall it is adaptive in nature. And here you are viewing a diagram, and this diagram, from this we can able to know these are the samples and the symbol rate with the delay and taps, with each one will be taking the value of the received input with its delay rate with 1 bit duration, and that will be combined here, that is added, and finally it pass on to the next level. There again, here it is the delay, so we can use the word delay or we can use the word 1 by Z. So here the values will be taken on with the values of YK, then getting incremented with all the sessions with the previous complex conjugate values are taken, and based on these are actually the filtering coefficients here. And finally coming to this part, what is the main thing is all these combinations are actually being summed up, and we need to extract the output. So output here, the desirable level of the output we mean here is actually dk. So dk is the desired value of the output. But to get that, we need to make this equalizer to operate. So here what happens, the equalizer will do the sampling based on the symbol rate, and usually it will do the correction based on the percentage of the error we get here between this dk and this dk bar, because we know that the difference in between the actual output and the desired output. So dk bar, that will be gives the error rate EFT, and based on that error the symbols, this weight adjustments will be done here with the complex conjugate values in the duration, that is T0 plus IT, with the number of taps, that is n, or we can say like n is equal to n1 plus n2 plus 1, likewise incremented based on the particular aspect of the content. And finally here what we make is the output of the filter we normally represent by the form, that is by the expression dk is equal to summation, that is minus n1 to n2, then cn star into yk minus n. Here the cn star represents actually the complex filter coefficients, that represents the complex filter coefficients, and or we can use the word that is weight factors or weighting filter coefficients, and the dk bar is output at the particular instant of time, and the input sequence are now arriving with the yk sequence. And also now finally we can able to, based on this, we can able to estimate the minimum that is expected level of the error rate. So expected error rate we can express by the word that is minimum mean squared error. So minimum mean squared error can be given as the expected value, so E of error square E of n square for this kind of the linear equalizer can be expressed as E of error square En square equal to t by 2 pi minus pi by t2 plus pi by t into n naught with the error rate, because signal to noise ratio, that is the main thing here, expressed in the frequency response format f of e power of j omega t square plus n naught. So where from this this term is the important thing in the frequency domain we are expressing, so we are putting the term with respect to the time duration, so f of e power of j omega t, and everywhere we normally represent the noise, that is n naught. So now coming to the non-linear equalization. So in the non-linear equalization, the main thing is here wherever we found that there is the distortions are heavy, that is too much distortion, in those areas we can only go for the option of non-linear equalizers, because with the linear equalizer we cannot able to adjust these weights accordingly for the errors, because error is too much, the error bits will be too much, and that we need to adjust. So in that category we are going for the term that is non-linear equalizers. So where we can see that much distortions are available. So in this category now we can name the type of the nonlinear equalizer. The name is decision feedback equalizer, and this equalizer we are using here in order to extract the output based on particular setting, and here in two phases things will happen. One is in the feed forward filter and one is in the feedback filter. So these two structures are not available in the normal linear equalizers. So now with this type of filter, there is a decision feedback equalizer, and here how the equalization is happening. Those are this section is for the equalization. So this is a place where we can think about based on the error value, predicted error value, adjusting the filter coefficients with the delay time, and in that proportionate obtaining the output. Then the decision device based on the threshold comparing actual output and the expected output. So when this dk bar is equal to dk, then we can say that there is no error. Error gets cancelled. That is, the error causing symbols are actually we have eradicated. Okay, so now in this regard we can say that the decision feedback equalizer, here the intersymbol interference which actually may happen in the future symbols, that can be estimated, and we can able to detect the further datas. So here the decision feedback equalizer which we have now, so this can be realized in the form of a normal equalizer pattern with the oncoming datas, with the delay and tap gains, and the complex conjugate values with the channel, with the transmitter. These things will be combined, and finally we are making to the output expectation. That will be matched out with the decision device here. If it is not equal, then again it will be made this fed to where? To the feedback filter. Then again, based on the error percentage, these all things will be happening. So the equalizer has here, as usual, the set of tabs like N1, N2, plus 1. So now, by adjusting the filter coefficients, the ISI can be cancelled and the future errors can be eradicated. So now, here we can find the term Fi. So this Fi star, these are actually the tap gains present in the feedback filter, and based on the previous decision and based on the previous results we got, we can able to predict the future contents. So the decay value, that is actually the output. So this output value should be decided based on the previous decisions, and the equalizer will be operated that way, and we can able to obtain the output. So here the feedback filter is driven by the decisions on the output of the detector, and its coefficients are adjusted in order to cancel the ISI on the current symbol from the past detected symbols. So again, we have an expression here that is for decay. So decay cap is equal to summation small n equal to minus n1 to n2, then Cn star, then yk minus n plus summation I equal to 1 to n2, then Fi dk minus 1. So this is expressed form of we can use the word that is the expression for the output of the filter. So this is the term which we have now, and finally, so these are actually noted or mentioned here based on the theoretical point of view, and finally we can say about the minimum mean square error of the decision feedback equalizer. So the thing is, when to decide the output, that is the main thing part here. That is why the name also decision feedback equalizer. So here, when we want to estimate the minimum mean square error of the decision feedback equalizer, here by using this formula we can able to estimate. This formula is as like the previous one. Here the frequency response, so we are representing, so f of e power of j omega t squaring plus these are actually n naught representing noise percentage in determining this expected value of the error sequence. So minimum, average, square error. Now the LTE, that is the linear transversal equalizer, will be well behaved when the channel spectrum is comparatively flat. That is, we know that normally the input symbols, that is the input data, that particular bandwidth is less when compared to the coherence bandwidth of the channel. We can say that the particular spectrum will be very flat. So this based on the performance of the DFE, we can say that this equalizer is more suited for severe distorted situations in the wireless communication channels. So thus we say that the decision feedback equalizer is getting more importance when solving the problem of ISI, which is considered as one of the main factor in communication systems, specifically in the wireless media. So that's all for your class today.